Hello there, my name is Angharad and I'm a second year, going into third year, engineering student here at Jesus College. Today I will be talking through some principles and techniques that engineers use when analysing different processes. If you decide to study engineering at university, you'll certainly become familiar with a lot of these ideas. And I hope that this lecture will give you a taster of sorts of what's to come and maybe a slight head start. Also, just as a disclaimer, my face is down the bottom right of the PowerPoint and I do occasionally block some of the information on the screen. I apologise for that. But I will try to get the lecture slides to you as a separate document as well. But failing that, I will be verbally describing what is on the screen underneath my face as well. So without further ado, my lecture today will be about control systems. And I suppose essentially systems in general. But I've decided to call it control systems because I'll be talking a little bit about systems that we like to control as well. So, just as a brief introduction, the main questions that I would like to tackle in this lecture are probably and most obviously what actually is a control system, and then once we understand the basics of what a control system actually is, I'll explain a few examples of control systems and what exactly makes it a control system. Later, I'll discuss some modelling techniques and explain how we control our systems. And then lastly, I will further contextualise these control systems and talk through a really interesting example, or at least I find it interesting, example of a control system. I hope you find it as interesting as I do, although probably by that point of the lecture you'll be sick of my voice, and if you want to watch it in double speed, then I'm sorry you feel that way. Right, so what is a control system? I think to answer that question, you need to understand what a system in engineering actually is. And I feel like we all kind of have an intuitive idea of what a system is, but I feel like the most easy way to describe what a system is to describe what a system does and then to look at some examples. So, a control system is something that we feed an input, then we allow the system to act upon the input, and then we expect some kind of an output. So underneath my face here, there's like a picture of an eye, and then underneath it says we observe an outcome. You're not missing much, don't worry. It probably seems quite obvious, but preferably we would like to be able to observe this output. Otherwise, we don't know whether our system is actually doing anything. And I think it's also worth explaining that when we talk about systems, there are kind of two main systems that we talk about, open systems and closed systems. And the easiest way to describe that, I've not added this in the lecture slides, but I just feel like it's useful to explain. An open system is one where external things can act upon it. I think most systems that we imagine would be open systems. And then a closed system would be kind of like an all-encompassing system. So maybe a good way of describing this would be the universe is a closed system. So everything inside the universe, or at least all the contents, are enclosed within the universe. So if we imagine all of the energy that exists is in the universe. Nothing new comes in, nothing from inside goes out. It just all kind of like transfers within this closed system. Whereas an example of an open system would be maybe my water bottle. We've got stuff inside it, we've got water, but if I put this on top of a heater, then we've put energy into our system. And likelihood is some heat will come out at some point if we take it off of the heater. So this bottle is a closed system. And I think the easiest way to imagine it is within a closed system, energy can't be created or destroyed. So within the universe, energy can't be created or destroyed, whereas in an open system, energy is coming from the outside and leaving, and doesn't necessarily have to be the same amount of energy, but generally within the wider system, so the surroundings, energy can't be created or destroyed, because normally a closed system or an open system is inside a closed system. That's why energy can't be created or destroyed. That was a bit of a tangent, but now that we have a vague idea of what a system is and a control system is, and what types of systems we have, I think we are ready to move on to some examples that are slightly more interesting than my water bottle. So, the first example is a mass spring oscillator. And I was thinking about this earlier, but I'm not sure how often you come across mass spring oscillators in A-level and GCSE, but we come across them all the time at university. So in case you've not been introduced to a mass spring oscillator before, as the diagram suggests, it's some kind of a thing with a mass. So maybe like, I don't know, a weight. You said, I have a weight of 5 kilograms. It's attached to a spring. I think you all know what a spring is. And then that's attached to a wall. And then when we displace this mass, we would expect the spring to pull it back in, and then it would kind of boing back and forth or oscillate. So our input is provided by an initial displacement. This in turn causes the system, or more specifically the spring, to possess some elastic potential energy. This energy is then dispersed through the system, and we're left with an oscillating output. So I suppose your challenge right now is this a closed system or an open system? I'm doing the door explorer thing where you can answer me, which I'm not going to hear you, but the answer is that it is an open system because we've put some energy in from the outside. So we feed an initial displacement, that is our input. We let the system operate, that is our process, and we observe an oscillating mass displacement, our output. Cool. So this example is very simple, a very simple example where we analyse the temperature of water in a bath. We feed the system with a heater, so that's our input. And it's our input because we can control the temperature of the heater by controlling how much power we supply it with. And then processes occur in the water, which cause the bath to get hotter. And then our output is an altered temperature, or altered water temperature. In this case of a heater, it's quite obvious that the water in the bath will become hotter. I think it's also worth saying that I'm very vaguely brushing over this processes part. But the easiest way to understand what that means is that your process in your system is almost always described, well, it is always described by a mathematical equation. I guess the question is, do we know what the equation describing the process is or not? And again, I'm not sure if at this point in your career you will have come across them, but normally things are described by ordinary differential equations at a lower level anyway. And then when things get a little bit more complicated, they tend to be described by partial differential equations, but it's essentially an equation that describes how things are changing relative to each other in a system. But I'm Not going to dwell on that too much. These are all things that you'll become very familiar with in time, and it just kind of comes with practice, understanding where a lot of these things come from. So my last example is an electrical example, and it's an example of an electrical motor. So here we supply some electrochemical energy, most likely from a battery. The motor performs a process that causes a rotating output. So battery power is our input. The motor performs a process which is described mathematically by some equation which I don't know, but I don't know, if you're cleverer than me, you might be able to work it out. And then we end up with a rotating part with some angular velocity, and this angular velocity is our output. So before I tell you how to manage a control system, it's imperative that we have an idea of how we can model a control system. So you're probably wondering how we do this, and we use something called a block diagram. Here is an example of a block diagram. It looks very complicated. I assure you it's not really that complicated, but I don't expect you to understand what's going on here. But I suppose just as a precursor to what I'm about to show you next, the general idea is that it's kind of a flow diagram, if you will. So we start with some kind of an input, which in this case we've called reference or steady state. And again, that will make more sense when I show you some graphs and stuff. And then this kind of describes an equation, but it's a more visual representation of an equation. And along each step we have kind of a different value. So where you see these arrows, sometimes we have some letters on top like A and V and X. Essentially, we have an acceleration, it goes through an integrator. What happens when you integrate an acceleration? We get a velocity. This velocity goes through an integrator. What do we get when we integrate velocity? We get a displacement. So it's essentially just kind of a flow diagram going from the left to the right, or from the end, the beginning of an arrow to the pointer of an arrow. And yeah, like I said, you don't need to worry too much about what it actually does or it's saying, but it's just kind of a visual representation of an equation, which you'll become very familiar with after, I'd say, your first year of university. But I'll admit, when we went through this in first year, I was very, very confused. It only really clicked in second year, and that's fine, you know. We all learn at different paces. I'm a little bit slow, but here we are. So let me strip it back to the basics because I feel like it was getting a little bit too confusing. So block diagrams map out our process from the back of an arrow to the front. So here you can probably understand that this sentence maps that our input enters a process, then the output exits the process. Well, a block diagram does the same, basically. We have an input going in at the start of this arrow and goes into a transfer function, and then it exits the transfer function as an output. And what a transfer function is, do you remember earlier how I was saying that you have a mathematical equation that describes your process? Well, that's essentially your transfer function. As a quick aside, this is something that is worth knowing, I suppose, when you get into your first year of university, but I wouldn't worry about it too much now, is that in our block diagrams, we don't tend to model using the time domain. We tend to use the frequency domain. And what that means is this block that's going to be underneath my face right now, I'll just read that out to you and then kind of explain. What the block says is, this means that our input, output, process are functions of frequency, not time. You will learn more about this in year one. But essentially what you do is you you map your time domain functions as frequency functions instead. So you essentially just convert them into a frequency function rather than a time function. And we do this using something called a Laplace transform, which is something you become very familiar with in university. You will use it all of the time. But essentially, I won't get into any of the maths of it, but essentially it converts from time to frequency, your process. And the reason we do this is because it just simplifies a lot of things down the line. So in the block diagram that we had in the previous slide, we had like integrators and just kind of all sorts of complicated things. Well, in the frequency domain, it looks very different. So like instead of having an integrator, you would just multiply it by a constant. But again, this is not something I want to get into right now. You'll see that it simplifies things when you study this properly. And I don't want to muddy up information for you for when you actually come to learn it. So, how do we manage these systems? Well, we use something called a controller. I'm mostly going to brush over physically what a controller is, but I think the best way to imagine a controller is that it is something that, I feel like this is just so obvious to say, but it's something that controls your output. And what this means is, physically, imagine you have, for example, I think a bridge is always a good example to use. Imagine you have a bridge that is quite flexible and it's very wobbly, and you walk over it and it starts to kind of wave around like this. A controller would maybe be something to help stiffen your bridge and change its properties a little bit. So you might want to put dampers in your bridge to stop it from oscillating so much when you walk over it. But yeah, essentially a controller physically is just something that you put on your system to manage how it operates, or to change that process step, I suppose. And this is what it looks like in a block diagram. So we have our reference coming in, and then our controller is kind of multiplied with our system or added to our system to help reduce effects that we don't want. And this alteration should hopefully move us closer to our desired output. So if I completely lost you there, don't worry, I will pull the reins in on the technicalities of a controller and try and explain qualitatively what we hope a controller will achieve. So we hope that our controller will drive us to the result that we want. So thinking back to our original examples with our water bath, we might hope that our controller will drive us to a certain temperature, or with our mass on a spring, we might hope that it will settle at a certain displacement away from the wall. But essentially we hope that our controller will drive it to that location, that temperature, that output that we want. And we hope that our controller will help this happen quickly. And we'd also hope that our controller will stabilize our system. You've probably not come across stability in this context before, but I'm sure you know what the word stable means. But I have included some graphs that might help describe what exactly we mean when we strive for stability. So our first graph on the top left is an input, so we'd often call this a reference, and this is what we tell our system that we want to aim for. So we say to our system, hello, we want to aim for this temperature right here. So if we say X is a temperature, so our system will go ahead and do its thing, and we have some overlay graphs here, and these are the outputs of our system. So if we look at the middle top graph, this is a stable system, and we know this because it eventually settles onto a steady value, and that steady value, thankfully in this case, is the input that we wanted. So our controller and our system is doing what we wanted. And then on the top left, we have this kind of like a ln kind of graph, but settling onto our input. This is also stable because it eventually reaches what we're after, and it eventually reaches a steady value. We would prefer the one on the right because it gets there. I'm not sure if it gets there quicker, but it doesn't have an overshoot, and preferably we don't want an overshoot. And what that means is, so you can see in the middle top graph that our output goes beyond the input that we want, and then back down, and then up and down, etc., etc. So that initial being driven beyond the input is called an overshoot, and preferably we don't want that. And then if we go down to the unstable graphs, for the output to be unstable, that essentially means that it doesn't settle onto a value and it kind of grows out of control, essentially. So I think a displacement example is probably the best way of describing this, but imagine rather than, your spring settling on a displacement, it just grows and grows and grows in its oscillations. Well, that would be unstable. Energetically, that doesn't really make any sense. We don't really expect that to happen with a mass spring oscillator. If it does, then wow, you've created energy from nothing. Congratulations, Nobel Prize. But yeah, we wouldn't expect that to happen. So yeah, we have this exponential kind of graph. That would be unstable because it doesn't settle onto a steady state value. And then we have this growing oscillations graph, again unstable because it doesn't settle onto a steady value. And then on the left over here, or bottom left, we have what's called a marginally stable graph. This is kind of irrelevant, but it's just interesting to say that this is when it's neither stable nor unstable. So it doesn't settle on something, but it doesn't grow out of control either. That would be marginally stable. But again, you wouldn't really expect this to happen either because energy dissipates basically. So at the moment, it can look like we're just looking at pictures of blocks and wiggly graphs and how is this even engineering? Why should you care about this? You came to see pictures of bridges, I get it. But this is the backbone of the cool engineering stuff that you see in the world. So what are the wider uses of these systems, you may ask? Well, pretty much everything. Well, within engineering anyways. So some examples of where we use control systems are obviously civil projects, most notably bridges, I think. I've already mentioned bridges, but in the background here we have a sketch of, I'm sure you recognise it as the Tacoma Narrows Bridge. Most GCSE physics teachers love to show that video. But if I remember rightly, what happened here was that the wind, I think, was blowing through the bridge at its natural frequency, and the bridge didn't have defences against this. So it started oscillating wildly out of control, and it couldn't withstand the power of the waves, so it ended up falling down. So in reality, we need to find controllers that will resist this kind of phenomenon from happening because it's dangerous. We use control systems in the agricultural sector. The next slide will feature an example of this, so I won't give any spoilers at this current time. But yeah, it's used in IT, the aeronautical sector, fluid mechanics, robotics, energy and environmental management, and so much more. Basically, everywhere you have engineering, you have control systems, because essentially the job of an engineer is to make a thing and control it to make sure that it's safe. So a really cool example would be the Archimedes screw, or at least I think it's cool anyway. Originally, this was used in agriculture to pump water and grains from a lower reservoir to a higher reservoir, because moving water is a really arduous task and you don't really want to do that by hand with buckets. So some very clever people, Archimedes, very clever person, managed to come up with a system to move things from a lower reservoir to a higher reservoir with minimal energy. So I'll just play this little video. It'll show what's happening. So you can see that it takes the water from a lower reservoir to a higher reservoir. In my next slide, it's a nice little quote from Archimedes. In my next slide, I will attempt to explain how this works, how we do this. Oops, oh dear, I'm playing the video again. You don't want to see it again. Right, so how does it work? This GIF kind of shows what we just saw, but we turn the screw using a handle or a crank, if you would rather, and this is our input. The fluid or the grain or whatever you're moving gets trapped between the enclosure, which is this like cylinder bit, and your thread. And with each rotation, the threads essentially start to move up, and then our fluid is released at the top, as you can see. So essentially, our system has converted kinetic energy from turning the handle to gravitational potential energy. So yeah, the water at the top has a higher gravitational potential energy than the water at the bottom. And it's just a really efficient way of moving water, and it helps to relieve strain. You can imagine carrying all that water up with buckets is hard work, and no person would really want to do that. So, I know what you're all wondering, can we use this to save the planet? And yes, we can. We can generate electricity using this idea. And the best way of imagining this is to imagine if we take that system and we operate it in reverse. So this is called a hydropower station. And essentially, can you see my large arrow on the top left there? Well, that is pointing to an Archimedes screw, except it's happening in the reverse order of what we've just watched. So instead of us turning a crank, causing the screw to turn and lifting water up, the opposite thing is happening. Water is moving from a higher reservoir where it has gravitational potential energy through the Archimedes screw down to the bottom where it will have a lower gravitational potential energy. And then this energy loss is converted, or energy loss in the water is converted to kinetic energy in the Archimedes screw. So it causes it to turn it drives it around in the opposite way to how turning the screw pulled the water up. And then that crank that we had at the top would turn around on its own. And then we can use the turning of that crank to operate a generator and hopefully charge a battery or power some homes. And this is a way that we can provide electricity to homes without burning fossil fuels, which is phenomenal. And if you're interested in knowing if this is actually used, it actually certainly is. I went to go and visit a hydropower station in Oxford the other day called Oseney Lock, and essentially it does this. In a lock you have a changing height of water in a canal. So where the water changes height, it passes through this Archimedes screw, it causes it to turn, and then that kinetic energy is transferred to electrical energy using a generator. And yeah, when we went to go and visit this, the person operating it said that it could fuel up to 60 homes, which is very, very, very cool because it's a very small power plant as well. If you imagine, I don't know, the size of a garden shed, it was probably about 2 of those, the building. Yeah, the Archimedes screw itself was quite small. It just had to be big enough to transfer the water from the top reservoir to the bottom reservoir, and obviously depending on the height change of the water, you'd need a shorter or a longer Archimedes screw. But it's also worth thinking, if there's a larger change in height, then there's more potential to generate more energy. So yeah, if you can try and think of places where you have a large height difference of water, maybe you could see if you could think of ways to associate or incorporate an Archimedes screw into that kind of situation, maybe a waterfall or something. Have a think about it. But obviously, with everything, these have limitations. It requires a certain amount of rainfall to come for us to be able to use the hydropower station. So, for example, the water in Oxford is diverted through all sorts of different paths. I think it comes from the Thames, it has to go through a canal, and then this hydropower station was on a little kind of off-road, I suppose, or what would you call it, off-river, I suppose, from the main thing. And it was the last priority for it to go through there because it's more important that you can still allow the water in the river to flow in the way that a river should naturally flow. So yeah, it's important when you come up with ideas for generating electricity to think about the limitations as well. Another limitation, which seems quite obvious, is where do the fish go? I'm sure if you do some research into these, you'll find that they have, I believe we were told there was kind of an underpassage underneath for fish to go through. Also, they require a lot of maintenance. There's a lot of rubbish in rivers these days, which is disappointing, but not just rubbish, scum, branches, all sorts of things that can get stuck in your screw. So it's important to try and think of ways to manage all of these problems that can happen. So for example, if you could maybe kill 2 birds with 1 stone and try and trap rubbish that's in the river while generating electricity, I mean, you could really be on something there. But at the moment, that is not what happens. It is just kind of relocated because most of it is natural debris. But unfortunately, that does mean that some unnatural debris can be relocated back into the river as well, which is not ideal. So yeah, just some things to think about there. So you can breathe a sigh of relief. I've come basically to the end of my lecture. Before I let you go, I thought it would be fun to leave you with a few short thought experiments. So my question for you is, if we can reverse a procedure for lifting grains to produce electrical power, what other systems can we reverse to generate power, and how can we use nature to exploit this phenomenon? So to kind of draw this back to our example, we looked at the Archimedes screw that lifted grains. So we put some elbow grease in to move some grains from one location that was energetically more favourable to a location that's energetically less favourable. And then we turned that idea around and we thought, okay, so if we can take something that's moving from a less energetically favourable location to a more energetically favourable location, how can we use that change in energy or exploit that change in energy to generate electricity? And we could find ways in nature to do that as well. So, for example, rivers that have changing levels, we could exploit that to turn our Archimedes screw. We know that locks have changing levels, so we can use that through our Archimedes screw. So I suppose just try and ask similar questions of what systems can we reverse to generate electricity? And then thinking about what kind of thing we would need to drive that, where could we find something similar in nature? So I guess another example would be a wind turbine. Is we know for a generator we have to turn stuff. I won't get too much into what a generator is, but I'm sure most of you have done this in triple science GCSE anyway. But essentially we want to turn something around that will create or cause this flux cutting in your electromagnetic field. Sorry, getting technical. And then we will produce some kind of a current from that. So we thought, okay, wind moves. Can we get wind to push round a wheel or a turbine to turn these things to generate electricity or to turn the rotor part of a generator? And yeah, we've managed to. So whichever way around you want to think about it, you can either think of a process that you can reverse to generate electricity, or you can just look out your window and think what happens naturally that we can try and exploit to generate electricity. And then some other environmental problems that we can consider and that you can try and mull over yourself to come up with ideas are clean energy generation. So obviously this is what we've just been covering. So can you think of more ways to generate clean energy? So not burning fossil fuels, and ideally, if we can, not using radioactive substances. So obviously, nuclear power stations. It's a bit questionable whether they're green energy or not. But if you can find ways of generating electricity without these horrendous side effects for the planet, that's just something we're thinking about. Fixing the damage that we've already caused. So I'm sure you know that the release of greenhouse gases has caused depletion of the ozone layer and just general environmental or global warming. So can you think of just ideas to reverse the process that we've already caused? This kind of ties into what we've been doing, is we're doing something one way, how can we reverse it to kind of oppose the effect that we've caused? Cleaning up the oceans, again, we've kind of discussed this with the river problem, the rubbish in the river, but can you think of ways that we can engineer some products to help clean the oceans? Again, we need to consider the negative effects of what we're doing. So, for example, I saw this video of this kind of like bin floating in the water, and it sucked water through and trapped rubbish from the ocean and then let the water back out. So it was kind of like pumping water but trapping the rubbish at the same time. But what would that do to the fish? So we need to try and think pragmatically about how this could affect more than just the problem that we're trying to tackle? Is it going to create other problems as well? Um, Excess production. So this is a problem of fast fashion, maybe, high demand for new stuff. Can you think of ways to tackle these problems? How we can maybe change the demand for products, and how we can recycle things that we've already used. Single-use plastic products. This is also a large problem, especially in COVID times. I'm sure you're aware that there are just masks and gloves and things being binned left, right, and centre. A lot of sanitary products obviously can only be used once. So can you think of ways that we can engineer solutions to this? Can we find ways of reusing single-use products, even though in the name they're single-use? Waste disposal. So again, nuclear waste, this is a problem, but just generally landfills are a problem. Can you think of ways where we can use this rubbish that we're filling land with for something useful? And limited clean water. This is a problem that I think we can take for granted in this country. It's raining as I'm speaking right now, but rainwater it's clean, it's not filled with salt. Is there a way that we can more efficiently use this water? Because in some countries there's not enough water to grow plants, or irrigation is causing damage to rivers. Things like toilets, they're wastefully using clean water. So can you think of ways that we can recycle used water and use it for processes where we use clean water but we don't necessarily need clean water? So yeah, these are all just things to think about. Feel free to contact me if you have any ideas or any questions at all, be it about the lecture or just general questions about Oxford, admissions, life at uni, engineering, anything at all. It's COVID times. I pretty much live on my computer, so I am more than happy to answer questions and queries. I hope that you will enjoy the rest of your summer school, that you have a good week. And yeah, just let me know if you need help with anything or any questions. Bye.